Hello. In this video, I'm going to talk about our Approx 2017 paper. This is a pictorial representation of the Facebook graph. It has 2 billion vertices and several hundred billion edges. According to my back of the envelope calculation, that's 800 GB of data and it will not fit in your random access memory. So if you want to compute something on this graph, we want algorithms that can handle the input sequentially and use sublinear amount of memory, and streaming algorithms are exactly that. A matching in a graph is a subset of edges such that each vertex has at most one edge incident to it. And in the maximum matching problem, we want to find a matching of largest size. Now, non-bipartite maximum matching problem has played a key role in the development of the field of combinatorial optimization, and also matching theory has won computer scientists their only Nobel Prize. Now we want to study the maximum matching problem in semi-streaming model. So let's quickly see what this model is. As mentioned earlier, we have sequential access to the input. So here we can think that edges arrive in the stream. For example, V2, V4 comes first, then V2, V3 comes, and so on. Our algorithms make one or multiple passes over graph streams, and ideally we want as less number of passes as possible. Now in the semi-streaming model, you are allowed n polylog n amount of space, where n is the number of vertices, and our algorithms use n log n amount of space. Please note that this much amount of memory is needed to store a maximum matching. Now maximum matching problem is well studied in the streaming setting. So a half approximation is trivial. You just maintain a maximal matching. How do you do that? You just keep a running maximal matching in the graph that you have seen so far. So you start with an empty matching, and as you see a new edge, you try to add it to the maintained matching. That is, if there is no edge in the current matching that intersects with it, with the new edge, then you just add the new edge, and this keeps a running maximal matching. Now why is this half approximate? Now each maximum matching edge intersects with some maximal matching edge, and each maximal matching edge intersects with at most two maximum matching edges. So that's an argument for half approximation. Now in one pass, Kapralov showed that you cannot approximate this problem better than 1 minus 1 by e ratio if you are allowed only semi-streaming, that is n polylog n amount of space. If you are allowed multiple passes, then you can get a 1 minus epsilon approximation in constant number of passes, where this constant depends on epsilon. Now even if you allowed just two passes, then Konrad, Magniez and Matthew showed that you can do better than half, and in this work we are going to improve their results. We'll see exactly what we prove towards the end. But even if we change the model slightly and consider a vertex arrival model where you have bipartite graph as input, and vertices on one side arrive with all their incident edges at the same time, then you can do better than half. So Karp Vazirani gave an online algorithm, which is also a semi-streaming algorithm, that gives you a ratio of 1 minus 1 by e. That algorithm was randomized, and Goel Kapralov Khanna gave a deterministic algorithm in the semi-streaming model in the vertex arrival model. Now a big open question in this area is can we do better than half in just one pass? That is, can we beat the trivial half approximation algorithm that just outputs a maximal matching. Anyway, moving on to the multipass results that we are going to show. This is our strategy. You start with a maximal matching, let's say this red edges, and there are some free vertices. Then in the later passes, you want to do three augmentations. You do that by finding a vertex disjoint set of three augmenting paths as shown, and you just augment the maximal matching. Now the idea is that if there are not many three augmentations for the given matching, then your matching is close to 2 by 3 approximate. Before seeing our algorithm, we want to see this small lemma. Now as you saw, you start with a maximal matching M0. Now consider a maximum matching M star. Now you can you can fix this maximum matching M star for the rest of the talk. So let's say size of M0 is half plus alpha times size of M star. Since M0 is maximal, we know that this alpha is non-negative. Then we say that number of three augmentable edges in M0 with respect to this M star is at least half minus 3 alpha times size of M star. Now we'll see some examples and give intuition for this. The proof is not long, but the intuition is more important. So let's say you start with this maximal matching M0 red edges, and all the edges are actually part of three augmenting paths. Then M0 is exactly half approximate. So here below the figure, size of M0 is half the size of M star, and the number of three augmentable edges is all of M0, which is half the size of M star, and that matches the lemma that matches what the lemma says above, which is it is half minus 3 times 0 times size of M star. Now on the other extreme, if none of the maximal matching edges are part of three augmenting paths and all are part of five augmenting paths as shown, then this is 2 by 3 approximate. Size of M0 is 2 by 3 times size of M star, which is half plus 1 by 6 times size of M star, and the number of three augmentable edges, this is the worst case, so it could be, so it's 0 in this case, which is half minus 3 times 1 by 6 times size of M star. Now the idea here is that if you start with a really bad matching, maximal matching, which is like about half the size of maximum, then there are lots of three augmentable edges, and our algorithms will find some good fraction of them. But if your maximal matching does not have many three augmentable edges, then it's already good. It's already so in this case we saw this extreme, it's already 2 by 3 approximate. So we don't have to do anything. So this is the intuition. Now we'll see our algorithm. So again we start with a maximal matching M0 in the first pass, which is as shown, and these are the free vertices that are unmatched by M0. In the second pass, you maintain this set of support edges which are shown in orange color. So what are the support edges? So the property of the support edges is such that all the unmatched vertices have degree at most lambda, and all the matched vertices have degree at most 1. Now how do you find this in the second pass? You just greedily maintain such a set. So if a new edge comes, you try to add it to the set of support edges without violating these constraints. If you can add it, otherwise ignore it. Now once you have this set of support edges at the end of the second pass, you do greedily three augmentations. So you think of like you go from top to bottom over this maximal matching M0 and try to augment it using the support edges. If you can augment it, augment, otherwise move on to the next. So that's it, that's our algorithm. That's a two pass algorithm. Now we'll analyze this. So here I'm showing three augmentable edges with respect to an M star. The M star is not shown, but assume that these are the three augmentable edges. Let's call these this set E3. Now I've shown their set of bad three augmentable edges. Why? Because so not both endpoints of those edges have a support edge incident on it. So the rest of the three augmentable edges are good because both their endpoints have a support edge incident to it. Now we call the bad set EB and the good set EG. Now I'm showing you M star. So all the three augmentable edges have are part of three augmenting paths with respect to this M star. Now, so okay, let me go back. Now the bad edges, for each bad edge, at least one endpoint of the bad edge, the M star edge incident to it was not added to support to the set of support edges because there were already lambda edges incident to it. So for example, I've shown here lambda support edges due to which the black edge incident to that vertex was not added to support edges, and that's why the corresponding edges are bad. So this gives us a lower bound on the set of support edges. So I'm just reducing the size of the figure because I want to analyze it below. So this gave us a lower bound on the set of size of support edges set, which is lambda times the number of bad edges, and there is a trivial very loose kind of upper bound which is 2 times size of M0 because each M0 edge can have at most one support edge incident to it. Now using the fact that size of EB is size of E3 minus size of EG, we get the next step. So I just changed the figure because I want to use it, and then again we use size of M0 is equal to half plus alpha times size of M star, and uh, using the earlier lemma, the number of three augmentable edges is equal to half minus 3 alpha times size of M star. We use this two in the above to get the fact that number of good edges is at least this much. This is just algebra by substituting what's above. Now the number of three augmentations is at least the number of good edges divided by 2 lambda, because when you do greedy three augmentations, for each augmentation that you do you can lose at most 2 lambda other augmentations. So if you do an augmentation A U V B, then you could lose potentially lambda minus 1 other support edges incident on A and lambda minus 1 support edges incident on B that could potentially land on good edges, right? So the number of augmentations is at least what's shown at the bottom of the slide. Now before analyzing how good this output is, we want to make a small digression, a couple of small digressions actually. So the earlier analysis could fail for general graphs because even if all your edges are good, they might form such triangles as shown, and it actually doesn't give you any augmentations. So what you do is you maintain the set of support edges like shown. So instead of allowing just one support edge incident on an M0 vertex, we allow two, and this fixes the problem, and the analysis goes through without much change. So the ideas in the analysis remain the same. Another thing to kind of optimize the algorithm is what we call live augmentations. Let's say this is the state of your support set of support edges at some point in the second pass. Now these two new edges show. First the top dash edge shows and comes in the stream, and then the one below comes in the stream. Now our algorithm will add the top dashed edge, and then it will have to ignore the next one. But then we are going to lose one augmentation in the third edge from the top. So what we do is when we get the first dashed edge, we ignore it because we know that we are going to augment using the right top free vertex. So we ignore it and we just add this edge, the one below, and then we get two augmentation. So this way we get a better approximation ratio. Now we analyze, find out how good the solution is. So we found out that we assume that after first pass we get half approximation m0, and we assume that m0 is half plus alpha times m star, and then after second pass uh, the number of augmentations were the second term in the right hand side. So the total matching size is size of m0 plus the number of augmentations, and simplifying this we get this bound, and since 1 minus 3 lambda plus 2 by 2 lambda square is non-negative, we get this bound. Now just put lambda equal to 4 and we get a half plus 1 by 32 approximation. So this is a two-pass algorithm for general graphs. Now we want to extend this to multipass. So we observed that if we start with a half plus alpha approximate matching, then we get a half plus this term, these two terms approximate matching at the end of the next pass. So you can just repeat this process. Start with after the first pass your alpha 0 is equal to 0 and you have a half approximate matching. After the second pass you have half plus 1 by 32, so your alpha 1 is 1 by 32, and then your alpha 2 is as shown, and we keep doing this, and then at the end of ith pass you get half plus alpha I approximation where alpha I is as shown. So this is a recurrence relation. What we do is, what I did was just plotted this in the program. So we start with if you see the fourth line, alpha is equal to 1 by 32 after second pass, and for I in range 3 to 100, which is we want to compute the recurrence from pass 3 onwards, and we use lambda equal to 4, which we found to be a good lambda earlier, and this alpha is just the recurrence that I showed on the last slide. It turns out that this is not good because then it converges to only half plus 1 by 14. So after playing around for a while, I realized that if you use lambda is equal to pass number, that you increase your lambda as the number of passes increase, then it converges to half plus 1 by 6, which is what we wanted. And once we know that we need to use this lambda, then we can show by induction that the relationship between the pass number and the approximation ratio at the end of that pass. We'll see the precise result on the next slide. So these are our results. So Isfandiari, Hajiagai and Monimizadeh independently showed using similar techniques these results. Oh, so this table actually shows advantages. These are not approximation ratios. So by advantage 1 by 12, I mean the approximation ratio is half plus 1 by 12. So we give algorithms for triangle free and general graphs for 2 and 3 pass. These are shown in this table, and the multipass result is shown in this table. So we get a 2 by 3 minus epsilon approximation in 4 by 3 epsilon passes. So if we ask the question, so what is the best deterministic algorithm for getting a 2 by 3 minus epsilon approximation, then our algorithm answers this question. So to conclude, we'll see some open problems. So can we give better 2-pass algorithms, and this could lead to better multipass algorithms. And on the lower bound side, Guruswamy and Unak showed that exact maximum matching cannot be computed in log n by log n passes in the semi-streaming setting, that is using n polylog n space, but no lower bound for approximate matching, no multipass lower bound for approximate matching is known. Can we even show a lower bound for 2 pass? That's it. Thank you.